Okay, so here we go. I'm going to have to record here a discussion of the last bit of the material we didn't have time for. Again, this semester is the first time that I'm aware of that Duke has shorted us by one class meeting in a semester. So we're running out of time. Okay, so here we go. A quick reminder talking about what is the method of Lagrange multipliers, and ultimately this is constrained optimization. So an easy starter example, just as a reminder, is this right here. So there is a function that we want to minimize in this case. That is distance to the origin. In this case, I'm using distance squared because the minimizer for distance is the same as the minimizer for distance squared. It's a convenient little hack. So that's what we want to minimize. This is called the objective function. But there is also a constraint. Here's our constraint, and what we call the constraint function is this part whose level set describes the constraint. So the level set is a key concept there. In other words, we need to know what function is it that's required to be constant. This is called the constraint function. So in any constrained optimization problem, there is an objective function and a constraint function. So again, just as a reminder, going through some quick examples, feel free to fast forward if you'd like. With this example right here, we're trying to maximize volume. That's our objective. And we have a constraint that there is a fixed value of area. That is our constraint function. Okay, and then looking at this economics example here, if we have a small business of some sort, and I want to maximize productivity, that's going to be our objective function. That's what I want to make as big as possible. But I want to do so by, with the understanding that I only have so much of a budget. I only have a finite amount of money with which I can hire people, buy tools, buy materials, etc. So I have a budget. Whatever that budget is, that's my constraint function. Okay, so all of that said, here's our strategy. And like we saw in unconstrained optimization, there is an elimination tool that we're going to use heavily for this. Let's see, here we go. The elimination tool works like so. If these three conditions are satisfied, we can make an argument that eliminates this point A where we know that these conditions are satisfied. We can eliminate that as a possible maximizer. And thus I only have to entertain points where the argument fails. And just like in the unconstrained case, this is actually going to eliminate most of my points. Okay, so let me talk through why these conditions are important and how we conclude that a point like this is not the maximizer. Again, if you've already heard this in the lecture you watched, you don't need to watch it again. Suit yourself. Here's how the argument goes. I need the differentiability of these functions because I need to be able to do Chapter 2 calculus. And all of Chapter 2 calculus really only works if these functions are differentiable. So there's that. Second, why do I need the gradient of g to be non-zero? Well, the gradient of g, this is the gradient of the function whose level set I'm looking at. And recall from Chapter 2, which we know applies because this function's differentiable. Gradients are always perpendicular to level sets. And so this vector is actually going to define an entire line perpendicular to my surface. And having this line perpendicular to the surface at that point is going to be really important for the argument that we're about to make. So the reason that I need the gradient of g to be non-zero is so that its multiples will actually give me this line that I need to talk about. And of course, if the gradient of g were the zero vector, its multiples simply would not give me that line. So very important, I need for this gradient of g to be non-zero. Okay, that noted, third condition, we're going to look at, let me clean this up a little bit. That's good enough. Third condition, I need to look at my objective gradient, the gradient of f, the gradient of my objective function. And I need that to point off of that perpendicular line. I need it to angle off of that perpendicular line. In other words, I need it to not be a multiple of my constraint gradient. Conveniently, the constraint gradient being non-zero, its multiples are that entire line. Okay, so if these three conditions are satisfied, then the punchline is that this is my picture. My picture looks like this. And if this is my picture, then I claim it's actually pretty immediate to eliminate this point A as a possible maximum. Because, well, with my objective gradient pointing off of that perpendicular direction, there's going to be a direction that I can go that keeps me on my constraint set that will allow for this directional derivative to be positive, and therefore the function is increasing. So that's what I really needed all of this setup for. I needed all this setup so I can say, check it out. In that direction, my function is still increasing. If it's still increasing, it's definitely not a maximizer. Okay, so a little bit more trouble to have to go to be able to eliminate points with our elimination argument, but nevertheless, still a fairly convenient set of conditions to write down. These three conditions right here are what allow me to eliminate points. Okay, so just like in the unconstrained case, I'm now going to ask what happens if my conditions aren't satisfied. If these functions fail to both be differentiable, one of them would be not differentiable. If my constraint gradient fails to be non-zero, okay, well that would mean that the constraint gradient is zero. If my gradients are not multiples of each other, and by the way, very important, subtle but important, I need gradient of f not to be a multiple of the gradient of g. And which one I write as a multiple matters because of zero. Anyway, if this fails to happen, if these two things are not equal, then they would be equal. So if any one of these three conditions happens down here, any one of these happens, then I have a failure of my conditions up here, and therefore a failure of my argument, and I cannot eliminate such a point as a possible maximizer. So again, the big punchline then is we are interested in these three conditions here. We call these the critical points because these are the points that I don't understand. They might be maxes. They're the only ones that I can't eliminate as possible maxes. Okay, so these are our three conditions. Now a little bit of lingo, convenient lingo to be able to refer to these conditions. I call this the differentiability condition. I think that's pretty clear why we would call it that. This one is not going to be particularly clear why the term is what it is. It turns out that when the gradient of g is zero, for reasons well beyond this course, it's natural to describe these points as being degenerate. And basically what it means is that the surface, something really nasty and bad happens to the surface, or can happen to the surface if this is the case. So we're going to call that the degeneracy condition, and I won't be able to give you a motivation for that. Lastly, this condition here, before I tell you the name, I'll comment that this factor here, lambda, is known as the multiplier for, again, I think pretty clear reasons. This method is called Lagrange multipliers. Lagrange was the mathematician that first wrote this down. And so this being the Lagrange multiplier, I'm going to refer to this as being the Lagrange condition. Okay, so just to have names. Those are the names of our three conditions. So now we are ready to apply these this test, this set of conditions for critical points, and we're going to find critical points now in some examples. Okay, here we go. So first example, we're going to look to see if we can find the highest point on a certain surface with a given weird equation. So what is the point with the highest z-coordinate? So highest z-coordinate means that this is the function I want to maximize. This is my objective function because I want to find the point with the greatest value of z, so I want to maximize this function z. Okay, so let's see here. So now what is my constraint function? Well, keep in mind a constraint function comes about by identifying your constraint as being a level set of some function. Well, this is the function whose level set is our constraint. So I have now my objective function identified, I have my constraint function identified, and now we're just going to start playing the game. Okay, step one. We need to look for where either of these functions fails to be differentiable. Is either of these functions ever not differentiable? Nope. They're polynomials. Polynomials are differentiable everywhere. So we get no critical points from looking at that first condition. All right. Now, a lot of students forget to write this down. This is a mistake. It's an important mistake. Keeping in mind, y'all have heard me say this a million times, it's not about the answer at the bottom of the page, it's about the validity of your reasoning. Your reasoning is only valid if you actually seek out all of the critical points. And so each one of those steps, independent of which one leads to the actual eventual maximizer, each of the steps is important as part of the reasoning. So keep in mind, recognizing that there are no critical points from that differentiability condition is an important part of the reasoning. And so this mere fact, right, this mere little statement right here, just saying, hey, both of these functions are differentiable, is actually worth points. And so you were strongly advised to take them. Right? All you have to do is, certainly in a case like this where the functions are clearly both differentiable, just say so. And again, this is worth points. You could take a glass half empty point of view on this and say, oh gosh, I could lose points just for not mentioning this one little thing. But that's, again, that's a pretty cynical take. The positive-minded point of view on this is, hey, you get points just for writing down one easy, just for making one easy but important observation. So I encourage you to take a positive point of view on this. Okay, that said, let's go on now to the second condition. We need to look for degeneracy. We need to see where is the constraint gradient equal to the zero vector. And so, okay, here's our function g. Here's its gradient. Easy partial derivatives, nothing to it. A little bit of linear algebra allows you to rewrite that formula as a matrix vector product conveniently. In this case, won't always work out like this, but nice to rewrite it conveniently when the opportunity presents. Setting that equal to 0, again, our degeneracy condition is for the constraint gradient to be 0. That leaves us with this equation right here, and this is actually an easy old Math218 or 221, a linear algebra classic problem. This is a homogeneous system of equations. And there are some nice facts about homogeneous systems of equations. You could row reduce and look at pivots and make arguments like that, but very conveniently, even more conveniently, I think, this matrix, simply by computing the determinant, you can pretty easily notice that this matrix is non-singular, and non-singular matrices have only the trivial solution to their homogeneous equations. Okay, so we have a point here. We have x equals 0. And tempting to say that, hey, check it out. We found a point that satisfies that condition. We found a critical point, so it seems. In fact, we haven't. And this is a little subtle little point. Now you got to, perspective. Keep in mind what we're doing. We have a process of elimination going on here. We are trying to eliminate points on our constraint set. Right here again is our constraint set. I only need to eliminate points that are actually on the constraint set. If I am brought a point that is not even on our constraint set, it's already out. It doesn't satisfy the original statement of the question, right? So no need to declare that I don't know what's going on at a point that's not even on our constraint set. And so what we need to do before we declare this to be a critical point, I need to look at my constraint. There it is. And I need to ask, is this point here on my constraint? If I plug this in, does this equation work? And in fact, no, it doesn't. Right? Pretty easy to just plug in 0, 0, 0. And of course, the left does not equal to the right. This point is not on our constraint set, and so it's not a critical point because it's not something I have any need to understand. It's not even on the table, so no worries. Okay, all right. Now again, make sure to document your reasoning. Notice how terse I was here, and this is plenty fine, right? But you do have to document how you are arbitrating, what to do with a point like this when you find one. Okay. So feel free to be terse, but you do have to address it. All right. So we have talked through these first two conditions. Moving along, we will now entertain this third condition, the Lagrange condition. Gradient of f equals a multiple of the gradient of g. These things are already computed. Gradient of f has these coordinates. The gradient of g has those coordinates. The Lagrange condition, again, is that the green is a multiple of the blue, written over here now in terms of coordinate equations. So there's our Lagrange condition rewritten. And again, remember why are we checking these conditions in the first place? We're checking these conditions so that we can eliminate points that we actually care about, points that satisfy our constraint, because those are the only ones that matter anyway. So not only do I need to find points that satisfy this Lagrange condition, I need points that satisfy this Lagrange condition, which are on our constraint. So we actually have 4 equations here and 4 unknowns. So this is what we actually need to solve. This is our system. And now begins algebraic fun. And these can get a little ugly. This is actually a problem in test writing, is that when we come up with a Lagrange multiplier question, a constrained optimization question such as this one, we have to make sure that this system is actually reasonably tractable. It's something that we can do. And very often they are not. So it's like I say, a bit of a problem. But of course, any question that we will ask you in this course will be one that we have confirmed is reasonable one way or another. Okay, so how to solve this algebra. All right, now there's a temptation. A lot of students will make this mistake. The temptation to look at these first 2 equations and kind of cancel the lambdas and then argue that that means that these 2 equations are true, and then a little bit of easy high school algebra gets you down to these relationships, writing x and y as functions of z. All right, so that is tempting. This is premature. This employed some unestablished reasoning, some unsupported reasoning. And specifically, the mistake that I've made here is I just canceled these factors of lambda willy-nilly. Keep in mind, canceling is dividing, and you cannot divide by 0. So if I want to be able to do this, if I want to be able to, what I have in orange here, if I want to be able to turn these first two equations into these relations down here between x, y, and z, I need to justify that I can cancel those lambdas. I need to know in advance, before I do this, that lambda is not 0. So how do I know? What's going to tell me that lambda is not 0? And the convenient little first step that I can take is to look at this third equation right here. And notice that lambda here is a factor of 1. And there's therefore no way that it could be 0. Right, so all you got to do, again, is, it's an easy little first step. You have to doff the cap, recognize that, yes, in fact, we do know that lambda is not 0. And then having done that, then, yeah, absolutely, cancel those lambdas, no problem. And as we did before, these equations A and B now give us this, and this algebra gives us this. And again, so we get some nice progress here, I'll call it, towards solving this algebra. Okay, don't underestimate the importance of that, what I have in green there, concluding that lambda is not 0 before you cancel. All right. Okay, now how to proceed from here? Well, we're almost done. As it turns out, these conclusions here, I can plug into my constraint equation. My constraint equation then, rewriting x in terms of z and y in terms of z, rewrites this whole equation all in terms of z, which I can then solve for z. Now, a little bit of annoying algebra there. But you get two possible values for z. All right, and then what do I do with these two possible values of z? I need to figure out how to get x and y, but don't forget, we already concluded how to solve for x and y in terms of z. So I can take these two values of z, and I can plug them into here, and this tells me my x's, right? And this then tells me my y's. There and there. Okay. All right, and that gives me my two critical points. Okay, so that's how this example works out. We've applied the method of Lagrange multipliers to this constrained optimization problem. Again, all we did is we went through and we checked the three conditions, the first two of which were pretty straightforward, pretty immediate, and the third of which tends to have some annoying algebra in it, and that's the nature of the beast. Okay. All right, let's see two more examples. The next one has a lot in common with the first example that I just did. We want to maximize this function, so there's our objective function. We have a constraint that this equation, our constraint is that this equation here has to be true, which of course is already written as a level set, which means that I have here my my constraint function right there. So I have my objective function here and my constraint function there in light blue. Okay, and again, the couple of quickie little freebies. Differentiability is a casual glance. These are polynomials. Those are differentiable. No critical points. The degeneracy condition, also pretty quick. The degeneracy condition comes from looking where where the constraint gradient is 0. And again, that's going to be only at the origin. The origin, let's see here. You know what I'm going to do? Let me let you erase all of this. This happens only at the origin, which does not satisfy my constraint. And so again, this is not on C. It's not our problem. I don't need to eliminate it. It was never an option in the first place. Okay. All right, so again, those first two conditions tend to go quickly. But again, free points don't throw away the free points. Get your differentiability points. It's easy. Get your degeneracy points. It's pretty easy. Make sure to get those points. Okay. And here we find ourselves again at the Lagrange condition. Again, the Lagrange condition is just a matter of writing it down. I already know my two different gradients, so I copy those down in there. Don't forget your constraint. Your constraint comes along as part of the deal when I'm trying to solve the Lagrange condition. So in this case, this being a two-dimensional problem, now I have three equations with three unknowns. And again, algebra fun. How to solve this system of equations. And again, there's a tricky bit here. It's very tempting. And in fact, generally a good idea, in fact, to look at these first two equations and to say, hey, I'm going to solve for lambda in both of these first two equations, and whatever I get for lambda, the two different values that I get for lambda, it's the same lambda, and so these two results that I got for the same lambda must themselves be the same. Right? So very tempting, and again, this gets you down to some nice progress. We have a relationship between x and y. Pretty cool. And again, a little premature. Again, I kind of cheated here because I again divided by something before I knew it wasn't zero. Notice in the first equation in solving for lambda, I had to divide by x. I had not yet established that x was non-zero. In the second equation, I had to divide by y. I had not yet established that y wasn't zero. And these kinds of things are annoyingly, persistent. And when you're dealing with a fair amount of tedium in the first place, it's tempting to just say, you know what, I'm just going to ignore that additional tedium. But you can't. This is important. Your reasoning has to actually make algebraic sense. You will get wrong answers, furthermore, sometimes, if you ignore this issue. So please do be careful. Now, again, it's an easy fix. If I want to establish, so that I can do this reasoning here, if I want to establish that x is non-zero, well, just take x, consider the scenario that it might be zero, and plug it in and check it out. This first equation just straight up fails. This first equation turns into 1 equals 0. So x can't possibly be 0. This first equation, as much as tells you it can't, because it doesn't work. And then likewise, it's equally easy. If you want to entertain, could y possibly be 0? Well, plug it into this equation here. It fails. It just doesn't work. You get negative 1 equals 0. It's just false. So not that much trouble, right? All you got to do is write it down, just something like this, something very brief. Just point out which equations, demonstrate what you need. And with that established, now knowing that these are not 0, I can go ahead and divide as needed, thus solving for these lambdas as needed, and concluding that they're equal, and therefore concluding, further down the convenient relationship down here, x equals negative y. Okay, so again, don't get the cart before the horse. Do please make sure to watch out for these little issues. All right. And now it's again kind of all over with the shouting. Once you have this established, you plug it into your constraint. Right? Again, here's our constraint condition. Our constraint then turns into this, which allows you to solve for y. And again, knowing y, I can then conclude x, which then gives me my two critical points. Okay, all right. So the algebra works out a little bit differently in this case. The little landmines are a little bit different here, but different examples of the kinds of things that you can experience. And one last quick thought. Issues with dividing by 0 aside, this general strategy of solve for lambda in multiple of the given equations and set your results equal to each other, this pays off very often. This is a really good first step in most cases. Again, just be careful with the legalities of the algebra. Okay, all right, last example. Again, a constrained optimization problem. The function that I want to make as small as possible in this case, so I want to minimize, is distance to the origin. Again, I'm going to make this clever observation that the point that makes distance as small as possible will also make distance squared as small as possible. So I'm going to work with distance squared because it avoids the square roots, and it's an easy little streamlining of the question. Nice hack. I encourage you to keep this one in mind. Okay, so that is our objective function. Our constraint is this. Again, make sure to write your constraint as something equals a constant. That something is your objective function. So now we have a constraint function. I said that wrong. I'm sorry. It's getting late. That is your constraint function. So we have an objective function and a constraint function. And now again we proceed with our 3 steps, 3 conditions to check. Again, the first couple work out pretty easily in most cases. Are these differentiable? Why, yes, they are. So easy. Points. We just earned points. Don't leave those points on the table. Make sure you get those. All you got to do is recognize what is usually a pretty straightforward observation. Okay, second, degeneracy. Where is my constraint gradient equal to 0? Well, again, easy algebra. This happens only at the origin, which again does not satisfy my constraint. So, not our problem. We don't need to eliminate it. It wasn't allowed in the first place. So we're, again, 2 conditions down at this point. Now we just have to think about the Lagrange condition. As usual, the Lagrange condition is paired with the original constraint. Let's see here. Let me not get ahead of myself. Because after all, it is only points that satisfy the constraint that I need to worry about at all. And then you look at this, let's see here, this system, and it is very tempting to, again, kind of blow off the little formal details of, dividing by 0 and all these seeming just bothersome formalities. And to reason as follows. Very tempting to say, well, this lambda right here has to equal to 1. But wait a minute. This lambda has to equal to 1/4. It's tempting, therefore, to say that, hey, check it out. I don't even need to look at the other equations. Lambda cannot simultaneously equal to both 1 and 1/4. So there's no solutions. Very tempting. Again, but again, sloppy. Again, not okay. And in this case, actually wrong. This gives us a terribly wrong conclusion because of these, again, seems like kind of just, uptight formalities. But in this case, we've just missed a bunch of critical points. So, again, the problem is I divided by 0. When I solved for this lambda here and claimed that I got 1, what I was actually doing is I was dividing by x. I was assuming that x was non-zero. Not a fair assumption. X might very well be 0. Likewise with the second equation there. Okay, so again I have to break this down into cases, and in this case, I no pun intended, I do think it's convenient to notice that this is a way to break down our possible cases. These 3 cases consider all points except for the origin. There's a lot of overlap in those cases, but that's okay. This considers all the points except for the origin. We don't have to consider the origin. We've already eliminated the origin. So these 3 cases will do it. And it's a very easy little trio of cases to entertain. Even if there's a lot of overlap, convenience is more important than lack of overlap. Okay, all right, so let's take these cases one at a time. What happens if x is not 0? Well, why would I want x to be non-zero? Well, it's so that I can do what I want to do in this equation. I would like to be able to divide by x. And thankfully, knowing in this case at least that x is non-zero, I can, perfectly legal, divide by x. That does, in fact, allow me to solve for lambda. I get lambda equals to 1. Now, no contradiction. I can't say this is inconsistent with any other lambdas I've solved for because I haven't solved for any other lambdas. But what I can do is I can take this value, lambda equals 1, and I can plug this into the other two equations. And if this lambda is equal to 1 there, and if this lambda is equal to 1 there, well, then I can straight up solve for y and z. Y and z would both have to be 0. Right, if lambda is equal to 1. If 2y is equal to 8y, y has to be 0. And likewise for z. Okay, now that allows me to take yet another step. Whoops. If y and z are 0, I can plug these into my constraint. There's my constraint, and my constraint allows me to solve for x. X would then have to equal to either plus or minus 6. Okay, so in the case where x is non-zero, I have these two critical points right there. Okay, now same game. I'll go quickly through the next version. The next version of this is, let's consider case 2. Suppose y is non-zero. If y is non-zero, then I can look at this second equation here. I can cancel the y's because they're not 0. That then gives me what lambda would have to be. Lambda would have to be 1/4. If lambda were 1/4, I can plug in lambda equals 1/4 into that equation, and x and z would both have to be 0. And if x and z are both 0, then that plugged into our constraint tells me what y would have to be. And then altogether, this is another 2. Whoa, missed. Let me try that again. This is another 2 critical points. Okay, and then likewise with case 3, I bet you noticed the pattern. I'm going to let y'all think through case 3 for yourself. This, of course, is the conclusion, and you end up with yet another 2 critical points. So, in fact, on this question, when we're looking, again, reminder, we're trying to find the points on this ellipse that are closest to the origin. If you're not careful, right, about the whole cancellation business, if you kind of fall for this idea of a contradiction of lambda having to equal to 2 different values, you get no critical points. When in reality, just this matter of being careful means you actually have 6 critical points, not 0 critical points. So tremendous difference in the outcome of the question based only on the fact that we were just being really careful with the algebra. Okay, so I think this is a great example to end on. Please do be careful with the algebra. Make sure to remember that as you're going through these Lagrange problems that it's really just a matter of checking the 3 conditions, the first 2 of which are usually kind of easy little freebies. Make sure to get those points. It's easy points. Take them. Don't leave them on the table. And then the usually greater amount of effort that has to go into solving the Lagrange condition, and again, be careful with the algebra. It's easy to mess that up. Okay, and that does it, finally. Okay, so see you in class on Friday.